Hey, in this video, we're going to discuss some identities involving summations of binomial coefficients. In the past videos, we've seen a bunch of results that involve binomial coefficients in some way, like results where we look at the probabilities in various types of lotteries and games. And in general, binomial coefficients can be written as I've written it there in the second bullet, and we say that as n choose k. N choose k is just defined as the number of ways to choose k distinct objects from n distinct objects where order does not matter. And when I use the word distinct, that implies that there's no repetition. So in today's video, we're going to see several identities that use binomial coefficients, and most of them will involve summations of binomial coefficients. And we're going to see a few different ways to prove these kinds of identities. And for most of the identities, we'll see multiple proofs of the identities. For some of them, I'll leave the proofs to you as a problem. So some of the techniques that we'll see for proving identities. One of them is the binomial theorem. We'll see that in the video today. We'll prove that. Another technique, something new that we haven't done before, is what I'll call counting the same thing two different ways. And the third technique, we've seen a bunch of this one in the past videos. This technique is induction. We'll see that in this video. And like I said, most things that we prove in this video will have multiple possible proofs. And we'll look at multiple proofs for a bunch of them. And some of them you can find other kinds of proofs. So let's start with a pretty simple identity. N choose k equals n choose n minus k. And like most of the identities today, there's multiple ways to prove this one. So we can note that n choose k, this is the number of ways to choose k distinct objects from n distinct objects. Just want to emphasize, order does not matter. There's no repetition. And this is the exact same as the number of ways to exclude n minus k distinct objects from n distinct objects. So if we choose k distinct objects from n distinct objects, this is the same thing as excluding n minus k distinct objects from n distinct objects. The n minus k excluded objects being the ones that we didn't choose. And we can note that the number of ways to exclude n minus k distinct objects from n distinct objects, this is actually the same as the number of ways to choose n minus k distinct objects from n distinct objects. And that tells us, just by definition of the binomial coefficient, that n choose k equals n choose n minus k. So that's one way we can see that one. And another immediate proof of it is we can use the definition of binomial coefficient that we proved using factorials. So in an earlier video, we saw that n choose k equals n factorial over k factorial times n minus k factorial. And by commutativity of multiplication, that quantity is equal to n factorial over n minus k factorial times k factorial. And this is just equal to n choose n minus k by definition. So let's look at another identity. This one's very useful. It's called Pascal's identity. And it says that n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. And before we prove the identity, let's see something else that's named after Pascal. This is Pascal's triangle. And Pascal's triangle, we just write binomial coefficients in a triangle. So I'm going to write it in two ways. over here, I'll write it in terms of binomial coefficients. So each row is a value of n, and we list n choose k for each k from 0 up to n. So we start with n choose 0, and then we do n choose 1, and then we got n choose 2, so let's start with that. And we can see what each of these values are over here. So 0 choose 0 is just 1. 1 choose 0 is just 1. 1 choose 1 is 1. 2 choose 0 is 1. Saying anything choose 0 is 1. Same with that 3 choose 0. 2 choose 1 is 2. 2 choose 2 is 1. The 3 choose 1 is 3. 3 choose 2 is 3. 3 choose 3 is 1. And we could also do 4 choose 0, 4 choose 1, 4 choose 2. So 4 choose 0, 4 choose 1, 4 choose 2. So 4 times 3 over 2 times 1. So we got a 6 there. Over here is 4 choose 3. It's going to be the same as 4 choose 1 by our previous slide. We got 1 here. So that's a good start to Pascal's triangle. And we can observe that if you look at any two adjacent numbers in a triangle, like this one and this one, for example, you add them together, you get the number between them and under them. You can look at this one and this one. 2 plus 1, we got 3. 3 plus 3 got the 6. 1 plus this 3 gives us the 4, and so on. So you can do this anywhere in Pascal's triangle. And that's what this identity is saying up here, if you view it in terms of the triangle. So let's prove that identity. And like most of the identities in this video, there's a bunch of ways to prove this. So let's start with the n plus 1 choose k plus 1. This is the number of ways to choose k plus 1 distinct objects from n plus 1 distinct objects. Order does not matter. There's no repetitions. And another way we can view this, which we saw in an earlier video, is this is the same as the number of subsets of size k plus 1 of the set 1, 2, up to n plus 1. And we can split this number of subsets into two cases. So when we count this number, we can break up that count into two separate counts. Case 1 will be the subsets that include n plus 1. And if we want to count how many subsets that would include n plus 1, we can see that there's n choose k of these. Since it includes n plus 1 and it has size k plus 1, that means there's k other elements in the subset. And those k other elements must be from 1, 2, up to n. So that's why we get n choose k for case 1. Case 2 will be the other subsets, the ones that are not included in case 1, which is the subsets that do not include n plus 1. So you can see this is the opposite of case 1. These two, they're opposites. So there are n choose k plus 1 of these subsets. And why is that? Well, these subsets do not include n plus 1. They have k plus 1 total elements. And since they do not include n plus 1, their elements must be from the set 1, 2, up to n. So that's why we get n choose k plus 1 subsets for case 2. And adding them together, that gives us a total of n choose k from case 1 and n choose k plus 1 from case 2. And that's the number of subsets of size k plus 1 of the set 1, 2, up to n plus 1. And that gives us Pascal's identity. N choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. And there are multiple ways to prove this one. So I'll mention another way. I won't put the proof up on this slide because it's something that you can do from home if you want, optionally. And you can just write n choose k plus n choose k plus 1 in terms of factorials. And if you do that, you can use arithmetic to write that as the factorials for n plus 1 choose k plus 1. So now we're going to look at a very useful tool for proving binomial identities. And this tool is called the Binomial Theorem. And it's also a useful tool in algebra. You probably have seen it when you learn about polynomials. So we're going to see a simple proof of the binomial theorem to start out with. And for this proof, we will consider the product on the left. So this x plus y to the n, we're going to start with that left side, and we're going to try to get the right side. So this x plus y to the n, same thing as up on the top. We can write that product out. What does x plus y to the n mean? Well, it's x plus y times x plus y times x plus y, and so on, a total of n times. And then we multiply that out, and we see that each of the terms in the product, there are two variables in there, the x and the y. And when we multiply all of these factors together in this product, there's a total of n factors. When we multiply them together and expand out the product, we're going to get a total of 2 to the n terms. And why do we get 2 to the n terms? Well, we can see in each of these factors, there are two possibilities, the x or the y. And there's n total factors. And each term that we get is obtained by choosing either an x or a y from each factor. So that's a total of 2 to the n possibilities. Now, when we have this product expanded out, each term in the expanded product is going to have some power of x in it and some power of y. We'll call the power of x x to the j for some integer j. Now, if the term has x to the j in it, since we have a total of n factors, it means that the power of y in the term must be y to the n minus j. So the powers of the x and y in each term have to add up to n. And we can note that each of the terms in our product, and this is something I mentioned before, but it's important, each term is obtained by just choosing a single x or single y from each factor. So each term that we get in our product, let's consider a small example. X plus y times x plus y. Each term, when we expand this product out, is obtained by choosing x or y from each of these factors. So we get, if we choose the x and the x, we get an x times x. If we choose the x from the first factor and the y from the second factor, we get an x times y. If we choose the y from the first factor and the x from the second factor, we get a y times x. And finally, if we choose the y from the first factor the y from the second factor, we get a y times y. So we see here, when we had two factors, we had 2 to the n total terms when we expand the product out. And in each term, the powers of the x and y have to add up to n. I mean, n is equal to 2 here. You can observe that. And each of these terms we got, like I said, it's obtained by choosing an x or a y from each factor. And we could continue this example out with more x plus y, and it would be the same. Each of these factors, we would choose either an x or a y from each of them. And I won't multiply that out. I'll leave that to you if you'd like to do that. So here's a question. Let me clear that so it's visible. The question is, how many times does the term x to the j, y to the n minus j occur in the product? So when we look at the x plus y, and we got x squared plus 2xy plus y squared when we simplified it. So for example, when j equals 1, how many times does the term xy occur in the product? And when we write it out in expanded form, before collecting the common terms, it would be written out like this. If we order everything with the x's first and the y's second. So same thing. So how many times does the xy term occur there? Well, to count the number of times that the term x to the j, y to the n minus j occurs, all we have to do is count the number of ways that we can choose jx's and n minus jy's from the n factors. And I just want to emphasize here, the n minus jy's have to be from the factors that are not the factors that we chose the x's from. So when we look at these n factors up here, and from each factor, like I mentioned in this bullet, the third to last bullet right here, that each term only uses one variable from each factor. So how many ways can we choose jx's from these factors and then use the n minus jy's from the remaining factors? And since we have n factors and we can choose an x from any of these factors for the jx's that we're choosing. So any of the factors, any of the n factors can be used for the j factors that we're choosing. So we can make a total of n choose j choices. So we're choosing just jx's from these n factors. So that's a total of n choose j choices for our x's. Now what happens to the y's? Well, the y's are determined by the x's. So whichever factors we used to choose the x's from, that tells us the n minus j factors that contribute the power of y. So that gives us a total of n choose j terms in our product, which are equal to x to the j times y to the n minus j. And then when we collect the like terms in the product, so for example, in the case that n equals 2, when we take x squared plus xy plus y squared, x squared plus xy plus xy plus y squared, and we collect the common terms, we have an xy plus xy. We join them together to make a 2xy. So when we collect the common terms, the coefficient of that xy is 2xy, and in general, the coefficient of x to the j, y to the n minus j, like we saw in the previous two bullets actually, that coefficient is n choose j. And so when we collect the common terms, the product that we got, the expanded product, it becomes the summation that we see at the top of the slide. So the coefficient that we see of x to the I, y to the n minus I is n choose I, and we're just adding those together. And this is exactly the same as down here. The coefficient of x to the j, y to the n minus j is n choose j. I just used an I instead of a j up in the sum at the top. So this is one nice way to see that the binomial theorem is true. And here's a problem for you to think about, if you'd like. See if you can find another way to prove the binomial theorem. So for example, one other possible way that you might prove the binomial theorem is with induction. So that would be a fine way to prove it. If you can find another good way to prove it, that would be cool too. So let's apply the binomial theorem to prove some identity. Here's a good one that we can use it on. So the identity that I claim is that for any n greater than or equal to 1, we have n choose 1 minus n choose 2 plus n choose 3 minus n choose 4 plus n choose 5 minus n choose 6 plus n choose 7 minus n choose 8 plus and so on and so forth, all the way up to n choose n. So if n is even, it'll be a minus n choose n. If n is odd, it'll be a plus n choose n. And I claim that alternating sum is equal to 1. And we're going to use the binomial theorem here. With the binomial theorem, the summation goes from 0 to n. However, our summation here goes from 1 to n. So it would be useful to have some n choose 0 term in there. To put that term in there, we're going to add 0 to our sum, but 0 in the form of n choose 0 minus n choose 0. So n choose 0 minus n choose 0, like I mentioned earlier, n choose 0 for any n is equal to 1. So n choose 0 minus n choose 0 is equal to 1 minus n choose 0. And again, it's equal to 0 as well. So the sum that we're trying to evaluate is equal to 1 minus n choose 0 plus n choose 1 minus n choose 2 plus n choose 3 minus n choose 4, all the way up to n choose n. So that's the same as the sum of the top because I just added the 0 to it. 0 in the form of 1 minus n choose 0. I might even annotate that. So this box here is just 0, just adding 0. And then this sum here, that's the one at the top. So we can see that this quantity that I have in two boxes is equal to, well, we can shift the boxes around a little. So this one right here is just, instead of a box, let's put it in an oval kind of thing. That's our 1. And then we have a minus n choose 0, plus n choose 1, minus n choose 2, plus n choose 3, minus n choose 4, and so on up to n choose n. So I might make that oval a little smaller so I can get the minus out of it. And then we have a second kind of rounded box here. And that's what's giving us this summation down here. But let me make that box a little smaller so it's not blocking out the summation so much. Okay, and I'll include that minus in there too. Okay, so minus n choose 0, plus n choose 1, minus n choose 2, and so on up to n choose n. And we can write this as the sum from I equals 0 to n of n choose I times negative 1 to the I times 1 to the n minus I. Now, it's kind of weird how I wrote that. So let's see why I wrote it that way. So we can see already we have the n choose I terms. We have the n choose 0 here. That's our I equals 0. N choose 1, n choose 2, all the way up to n choose n. So I equals 0 to n. And we start with a minus, and we have a plus, minus, plus. So that's why we're getting minus 1 to the I. And when we multiply by 1 to the n minus I, this doesn't do anything because multiplying by a power of 1 is just multiplying by 1. And that is going to give you the same number. And the reason why we write it this way is because writing it this way gives us something in the form of the left side of the binomial theorem, or actually the right side of the binomial theorem. I guess you could write it either way, so one of the sides. And we can see by the binomial theorem that if we use a equals minus 1, so a equals minus 1, b equals 1, the sum I equals 0 to n of n choose I, a to the I, b to the n minus I, the binomial theorem tells us this is equal to a plus b to the n. And so we're going to use that with -1 and 1. So we get -1 plus 1 to the n. I'll clear that to make that a little more visible. And remember, we still have the 1 right here. So this quantity right here became a -1 plus 1 to the n by the binomial theorem. This one just came down here. And there was a minus in front right here of the sum, and that came down as well. So we can simplify that because -1 plus 1 is 0. So we get 1. And we can conclude then that the summation that we started with, n choose 1 minus n choose 2 plus n choose 3 minus n choose 4, and so on up to n choose n, this is equal to 1. So that was a pretty nice use of the binomial theorem. It gave us a solution that was only a few lines. Here's another identity. You've probably seen this one before, but it's a nice example of an identity that can be proved multiple different ways. So we will actually prove it multiple ways. Here's the first proof. Using the binomial theorem, like we did on the previous slide, we can write the sum I equals 0 to n of n choose I as the sum I equals 0 to n of n choose I times 1 to the I times 1 to the n minus I. So here we're looking at binomial theorem with a equals 1 and b equals 1, and we get a plus b to the n, and so we have 1 plus 1 to the n, and that's what we wanted, 2 to the n. We can also prove this using this technique where we count the same thing two different ways. So the thing that we're going to try to count here is the number of subsets of the set 1, 2, up to n. One way that we can count this is we can think of it like choosing or not choosing each element of the set 1, 2, up to n. In other words, for each element in the set 1, 2, up to n, we have a binary choice. We can either include that element in our subset, or we can exclude that element from our subset. There's a total of n elements, and we have 2 choices for each element. So the total number of choices we can make, in other words, the total number of subsets of 1, 2, up to n, is 2 to the n. So that's one way that we can count the number of subsets of 1, 2, up to n. Here's another way we can count it. We can break up the subsets into cases. We'll look at the size 0 subsets. Then we'll look at the size 1 subsets, then the size 2, the size 3, and so on all the way up to the maximum size n. And then we'll just add all those quantities together. So how many subsets of size 0? Well, there's n choose 0 of those. How many subsets of size 1? There's n choose 1. How many subsets of size 2? N choose 2. How many of size 3? N choose 3, and so on. And we just add them all up. And that gives us the sum from I equals 0 to n of n choose I. And again, this is the same quantity that we were counting before, the total number of subsets of 1, 2, up to n, which we saw before in this bullet was 2 to the n. So we just proved the identity by counting the same thing 2 different ways. And that identity, same one as the top, is the sum from I equals 0 to n of n choose I equals 2 to the n. Here's a problem for you to think about. And this one, like the identities we've seen here, has multiple possible proofs. So prove that n choose k is equal to n over k times n minus 1 choose k minus 1 for all n and k that are greater than or equal to 1, and they're integers. Let's prove another binomial identity. For this one, I claim that the sum from I equals 0 to n of n choose I squared, so it's kind of similar to the one we saw on the previous slide, except now instead of to the 1 power, it's to the 2 power. I claim that sum is just equal to 2n choose n. Why is that? Well, we'll use the technique that we saw on the previous slide. We will count the same thing 2 different ways. The thing that we will count is going to be the number of subsets of the set 1, 2, up to 2n, and these subsets must have size n. Clearly, this is equal to the right side of the equation at the top. This is 2n choose n. Now we just need to see why it's also equal to the left side. So we will count the quantity, the number of subsets of 1, 2, up to 2n of size n, by breaking it up into cases. And for those cases, we will take 1, 2, up to 2n, and we will split it in half. So we'll look at 1, 2, up to n, and n plus 1, n plus 2, up to 2n. And we're going to break the subsets into classes. So the subsets of size n from the set 1, 2, up to 2n, the class will be defined by the number of elements in our subset that are in the first half, right here, 1, 2, up to n. So in other words, for each j equal to 0, 1, 2, up to n, we will count the number of subsets of 1, 2, up to 2n of size n with j elements in 1, 2, up to n. So the number of elements that a subset of size n of 1, 2, up to 2n can have in 1, 2, up to n is anything between 0 and n. So that's why we're breaking it into these cases, a total of n plus 1 cases. And those total of n plus 1 cases, if we can count each of those cases separately, we can just add them up. So that's how we're going to try to get the left side, is by showing that that sum is equal to the sum of these cases. So we will look at the number of subsets of 1, 2, up to 2n of size n, which have j elements in the first half right here. So the first half, 1, 2, up to n. And I claim that quantity is equal to n choose j times n choose n minus j. Why would that be? Well, The subset has to have j elements in 1, 2, up to n. There's a total of n choose j ways to choose j elements of 1, 2, up to n. So that's what's giving us this n choose j term. Now, this subset is a subset of total size n, and it's a subset of the set 1, 2, up to 2n. If it has j elements in the first half of 1, 2, up to 2n, so j elements from here, it means that over here, if there's j over here, there have to be n minus j over here if it's a subset of size n. So if we have n minus j elements from over here in the second half, n plus 1 up to 2n, there's a total of n elements there, and we need to choose n minus j of them. So that's how we're getting this n choose n minus j term. And we multiply n choose j times n choose n minus j, because for any of the choices of j elements that we make over here, we can combine that with a choice of n minus j elements from over here. And we can note that n choose j times n choose n minus j, this is the same as n choose j squared, because n choose n minus j is equal to n choose j, as we proved on the earlier slide. So I claim that the number of subsets of 1, 2, up to 2n of size n is just equal to the sum from j equals 0 to n of n choose j squared. So we took the quantity that we got in the previous bullet, the n choose j squared, and we added it up for j equals 0 to n, because those were our n plus 1 possible cases for j. N plus 1 because we have n minus 1 down to 1, and then 0. So total of n plus 1 possibilities for j. And this is the left side of the equation. So we counted the same thing two different ways. The number of subsets of 1, 2, up to 2n of size n, it was clearly equal to the right side, and it was also equal to the left side, because we saw that we can break up the quantity in two cases and sum those cases up. And it gave us exactly that sum. So it worked out pretty nicely. Here's a problem for you. Can you find a different way to prove this? Like, for example, one way that might work pretty nicely is the binomial theorem. There might also be other nice ways to prove it. Okay, here's another cool identity. This one is useful to visualize with a picture so we can understand why it has this name, the hockey stick identity. So let me draw my binomial, my Pascal triangle, binomial triangle. So we got a few rows of it. Let's do. Okay, and then over here, start 1 up here, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And let's do one more, 1, 5, 10, 10, 5, 1. Okay, so the hockey stick identity. So let's look at a hockey stick here. Maybe I'll even do one more row, so we can have more hockey sticks. Okay, so here's one hockey stick. Here's one too. There's a good one. Oh yeah, one here too. Okay. Now let me put a line on each hockey stick just to make it a little clearer. Let's look at the numbers above and below the lines. So we got up here, first hockey stick I drew, we got 1, 1, 1, 1, 1, 1. We add them together. We got 6 there. We got 6 down here too. For this one, we got 1, 2, 3, 4, 5. We add them together, we get 15. Same as down here. For this one, 1, 3, 6, 10. We add them together, we get 20. And this small hockey stick, same property, 1 plus 4 equals 5. And the hockey stick identity says that for any hockey stick that we draw in the Pascal triangle, we always get this property. So let's see it written a little more formal way than that. So that's how we can write it. The sum from I equals R to N of I choose R equals N plus 1 choose R plus 1 for all N greater than or equal to R. So probably it'll be useful to see the other Pascal triangle again here. So if we form a hockey stick in this Pascal triangle, we start along this diagonal right here. So this diagonal, we pick some binomial coefficient along that diagonal, which is a term of the form R choose R, let's say. So we can do an R equals 1. And then we make some hockey stick. So we go up to some N, and we look at the sum R choose R plus R choose 1, or plus R plus 1 choose R, plus R plus 2 choose R. So here, R equals 1, we have a 1 choose 1, plus a 2 choose 1, plus a 3 choose 1. And we could keep on going if we had more rows. So maybe have an extra one here. So we look at these, and we just get a bunch of n choose 1s for n equals 1 up to 4. And we're claiming that's equal to 5 choose 2 if we take this hockey stick. And we could have looked at another hockey stick, so to have a 5 choose 3 here. We could take R equals 2. So R equals 2, we'd have a 2 choose 2 plus 3 choose 2 plus 4 choose 2. We could keep on going if we have more rows, or we can stop our hockey stick right there. And if we stop it there, we claim it's equal to 5 choose 3. So if we go up to n equals 4, we claim that the sum is going to be 5, and then choose 3, the 3 being our R value plus 1. So this is what we're going to try to prove, that the sum from I equals R to N of I choose R is equal to N plus 1 choose R plus 1. We can use induction to do a pretty easy proof of this. Our base case will just be N equals R. With N equals R, the summation only has one term. So the sum from I equals R to N of I choose R is just R choose R when N equals R. That's just 1. That's the same as R plus 1 choose R plus 1. So that's our base case. For the inductive step, we'll have this inductive hypothesis. We'll suppose that the sum from I equals R to N of I choose R equals N plus 1 choose R plus 1. And we want to prove the next step. So we want to prove that the sum from I equals R to N plus 1 of I choose R is equal to N plus 2 choose R plus 1. So to prove that, we can write that sum, the sum from I equals R to N plus 1 of I choose R, and then we can take the last term out of it. So we can write it as N plus 1 choose R plus the sum from I equals R to N of I choose R. That's going to be N plus 1 choose R plus N plus 1 choose R plus 1. And that's by our inductive hypothesis right here. So we just substituted with that hypothesis. And here we can use Pascal's identity. So we can add those two together. By Pascal's identity, we get N plus 2 choose R plus 1. And that completes the induction. So that was what we wanted to prove. And another way to prove this that we'll do is by counting the same thing two different ways. So the thing that we will count this time is just the number of subsets of 1, 2, up to n plus 1 of size r plus 1. And clearly, this number is equal to the right side of our equation. So the n plus 1 choose r plus 1 over here. That's clearly the quantity that we're counting. So we just need to show that the left side is also that quantity. And we'll do something kind of similar to what we did with the previous problem like this, where we break it up into cases. So this quantity, the number of subsets of 1, 2, up to n plus 1 of size r plus 1, we can break it up into cases depending on the largest element in the subset. So we'll define our cases CR, CR plus 1, up to CN. So these will be classes of subsets. All the subsets that we're counting are going to fall into one of these classes, exactly one. So these classes will be disjoint from each other. And the class CJ, and this will be for each J equal to R, R plus 1, R plus 2 up to N. The class CJ will consist of the subsets of 1, 2 up to N plus 1 of size R plus 1 that contain J plus 1, but they don't contain any X that's greater than J plus 1. In other words, the class of subsets CJ will consist of the subsets whose greatest element is J plus 1. And it's clear then that if CJ consists of the subsets whose greatest element is J plus 1, then the classes CR, CR plus 1 up to CN have to be disjoint from each other, because the subsets in those classes, if they're in different classes, they have different greatest elements. So the classes do not have any overlap between each other. We can also see that all of the subsets of 1, 2 up to n plus 1 of size r plus 1 have to fall into one of these classes. So in other words, all of the subsets of 1 up to n plus 1 of size r plus 1, their greatest element must be at least r plus 1. So if it was less than r plus 1, it would mean that it was at most r, and then it would be impossible for the subset to have size r plus 1. So the greatest element must have size, or the greatest element must be at least r plus 1, because the subset has size r plus 1. And so that's why all of the subsets must fall into one of these classes. So there's no subset that doesn't fall into any of these classes. And I claim that the number of subsets in the class CJ is equal to J choose R. Why would that be? Well, let's look at what CJ is. CJ right here is the class of subsets of 1 up to n plus 1 of size r plus 1, that's important, that contain J plus 1, but do not contain X for any X greater than J plus 1. In other words, the greatest element is J plus 1. So that's the greatest element in the subset. So these subsets have greatest element J plus 1, and they have size R plus 1. That tells us they don't have any element greater than J plus 1, but they must have J plus 1. Since they have size R plus 1, there are R elements besides J plus 1. And these R elements, they must be from 1, 2, up to j. Why is that? Because j plus 1 is the greatest element in these subsets. So they can't have any elements greater than j plus 1. So all of their other elements have to be from 1, 2, up to j. And they have r other elements because they have size r plus 1, and they have the element j plus 1. So the total number of these subsets is just j choose r, the number of ways to choose r elements from j elements. And all we have to do is add up the number of elements in Cj for each of the j. And when we add that up, let me clear that so it's a little more legible. When we add up and we have this summation, we get the sum. Since we started the Cj's at j equals r, and it goes up to j equals n, we can write this as the sum j equals r to n of j choose r. The j choose r, again, is what we proved in the last bullet, the number of subsets in Cj. And so we see that this summation right here, the sum from j equals r to n of j choose r, is exactly the summation at the top on the left side of the hockey stick identity. And the right side, like I said earlier, it's immediately clear that this is the quantity that we're counting, the number of subsets of 1, 2, up to n plus 1 of size r plus 1. So immediately that's n plus 1 choose r plus 1. And so that gives us what we want, the hockey stick identity. So we've seen a bunch of techniques for proving different binomial identities. Most of these we saw different ways to prove them. And in the next video, we'll see more involving binomial coefficients. Thanks for watching.